We will continue in the integration part, and what we have seen in the integration is that integration is nothing but calculation of addition. So it is a kind of other way to calculate the addition while calculating the area. So that is integration. If we want collection, net collection, addition, then we go either for multiplication or we go for calculating the area. If I have independent variable in along x-axis and dependent variable whatever the collection rate is, then we have the total collection as the area. Like if collection rate is 5 orange per day I am collecting, then at the end of 5 days I will have 5 plus 5 plus 5 plus 5. So that is 25 oranges or 5 into 5, or independent component is days, then 5 days and 5 orange per day is the collection, then area of the rectangle is 5 into 5. So, so three ways we saw that in addition happens, and integration is a way to find the addition through area. But integration comes in means integration is more versatile in a sense that the rate of change, rate of collection that what we see is constant, that is 5 orange per day. But if it is not constant and it is a function of independent variable, like if the days are d, then it is d square plus 2 1 plus d to the power q sine d or whatever. So the rate of collection is algebraic equation, polynomial equation, sinusoidal equation, trigonometrical equation. If those kind of scenario happens, then calculation of the addition through typical addition or multiplication is not possible. Then we go for calculating the area. So in 2D, where we have line equation, in that sense, the calculation, in that sense, the calculation happens through, in that sense, calculation happens through area. So if I have a line equation called t square, where t is the independent component, then the area underneath is t to the power 3 by t to the power 3 by 3. This is what we saw. So integration of t to the power n is t to the power n plus 1 by n plus 1. Differentiation of t to the power n is n t to the power n minus 1. It is called, so integration is also called anti-derivative. I would rather say that differentiation is anti-integration, because integration is the most basic thing on top of which we we have differentiation, then differential equation, and so many things that comes into the picture. Now, in integration, when we are talking about calculating the area while coming to addition, then in 3D, okay, in 2D, we have one independent component and one dependent component. Then it comes to 2D. Independent component and dependent component x and y, they come in one plane, that is surface. Now, whereas in 3D, okay, the addition is achieved through calculation of volume, when in 2D the addition is achieved through calculation of surface, calculation of area, then in 3D addition comes when addition happens through calculation of the volume, that is 3D. So if this is xy plane, then this is x axis and this is y axis, this is x axis, this is y axis. X is independent component and y is independent. If that is true, then fxy is z, that is vertical. Now, xy plane, we have so many x and y points. Against each point, we have fxy or zy. So, it is 3D, okay, surface and then vertical. It is 3D. Now, if we want to calculate the addition, then we have to calculate the volume. So, volume is vertical into area. In 2D, vertical into width, that is the area. Now it is vertical into area is volume. So if we calculate volume, then we are done with calculating the net addition. So that is integral calculus as far as 3D is concerned. Okay. Now, in 3D, there are two things that we saw. There are two branches. Okay. One branch talks about that when you are calculating, if this is the surface, if this is the XY plane, then XY plane, we would now it at the XY plane, if I see the fxy, at each xy, we have different value of fxy. Like if I take cone, then at this point, at this xy, the cone value is 0, whereas other xy, the cone value grows. So the z is dependent component on two independent component x and y. Z is related to xy through function over fxy, function over xy. So z equal to function over x comma y, z equal to fxy. Okay. Now, if we want to calculate the variation of z along x-axis, then it is dz by dx. Variation of z along y-axis, then dz by dy. So we are not going to talk those partial derivatives. Okay, we are not differentiating, we are integrating. We are calculating the addition. Okay, so now the one way of calculating the integration is, since at each, now this is xy plane, each point xy, now each point xy, now we have different z value. So now we cannot calculate one volume. So if I know the full area, width into, okay, one is width and one is length, because height is this. So width and length. So width and length, if I calculate, multiply them, I get the full surface area. But full surface area I cannot multiply with the height, because height are different at different x comma y. That is the situation. So any height if I take, then multiply by full area, it will not be appropriate. So what I need to do is, I have to divide the full surface into small rectangles. So many rectangles. At each rectangle, I have to check what is the fxy somewhere, because each rectangle will have a set of xy points. Maybe 100 xy point. Against each 100 xy point, fxy would be different. Any one we would take, probably the bottom left corner or right top corner, whatever in that rectangle. So if this is the xy plane, now xy plane, I cannot have full area into height, because height are variable, because it is function over x comma y. So height is variable at each x and y. So in that we have to divide the surface into small rectangles. If I divide the surface into small rectangles, then at each rectangle, if this xy plane had 10,000 xy points, then small rectangle will have less. So at each rectangle, suppose it is 100, then, or suppose it is 10 only, I divided into so many sub rectangles. Now it is 10. So out of 10 point, 1 point I have to select, for which I'll get the fxy. So that fxy into that small rectangle area. So whatever the volume I am getting, that volume I have to get for all the rectangles, and then I have to add it. That is the one way of integration. This way of integration is highly useful when we go for contours. So in contour diagram, we have xy plane on the paper. So a paper has xy plane. Against xy plane, now we have contours of the height. So if this is xy plane and vertical is fxy, then I'll make cross sections. Okay, at each cross section, like I have drawing a diagram of a hill. There is a hill. So hill, at this cross section, what is the height? At this cross section, what is the height? At this cross section, what is the height? So if I draw in 2D diagram, then the peak will be small rectangle, a small circle, circular kind of thing. Then bigger circle, then bigger circle, then bigger. The biggest circle will be the basement, and its contour height will be less. Slowly we'll proceed in xy direction, and contour height will grow. At the center we have very small circle, but its height will be very high. Now I have to calculate the volume of the hill. Okay, if I calculate the volume of the hill, the XY surface, I'll place so many rectangles, and in each rectangle, I'll see how many contours are falling. Now we'll take the average of the contour height and then that height into the rectangle area. That is the volume of that particular rectangle. Now I'll add all the rectangles. If I have divided it into 100 rectangles, then 100 rectangle into per rectangle's volume. If I add that, then we can estimate the volume of the hill. So this is calculating the volume or final addition through the approximation. This is one way. So what is good in this is the number of section that we do along x-axis and number of section we do along y-axis, the cut we make. Number of cut along y-axis is m. Number of cut along x-axis we do n number and m number. Then total number of rectangles what we receive in xy plane is n into m. So n into m should be as maximum as possible so that the width and height, the area of the rectangle is very small so that few xy point would fall, and then estimating the height in that rectangle is more accurate. So n and m tends to infinity so that the delta x and delta y, that is width and height, width and length of the rectangle, each rectangle what we get is tends to 0. So this is maximization in the approximation that we can do. The minimum what we can do, we will take full rectangle, only one rectangle, full rectangle, and for the height, some height will take. So certainly it is will be far away from the actual volume of the hill. Okay, so this is one way of calculating the integration, the volume through the approximation. Other way is if I know the equation of the fxy. So fxy is in term of equation. If it is in term of equation, then this is xy, this is x-axis, and this is y-axis. Now this is xy plane. If this is xy plane, then first we will calculate. So this is the area of a surface along x-axis, another area of a surface along x-axis, another area of a surface along x-axis, but they are at different y. Now this is area of a surface along y-axis, area of a surface along y-axis, area of a surface along y-axis at different x. So if I calculate the area of a surface along x-axis, okay, but this area will be in function of y, because this area would change depending upon the y. Okay, I would take example as suppose that this is a semicircle. I believe it is visible. So this is a semicircle. So semicircle is kept like this, where the base is straight line. You can say half circle, exactly half circle. So it is half circle with some radius and it is falling on the xy plane like this. So towards camera it is narrower, and towards me it is broader. So at the end it is a straight line. Okay, that is the kind of diameter at the bottom. So this is, suppose this is the case. Now if I calculate the surface area along x-axis and at the end, then it will be very small. Then it will become bigger. At the end where full diameter is there, the surface area will be maximum. Okay, since the arc is like this, okay, semicircle is like this, so at the front it is narrow, then it is slowly it is becoming bigger, and at the end it is very big. If I calculate the surface area, then at the front it will be very small surface, then slowly it will be bigger. This proves that the surface area along x-axis is function of y, it is dependent upon y. So when y is maximum, at that time surface area is minimum. When y is 0, when it is maximum, that y is 0, it is touching x-axis, y is 0. There it is surface area is maximum. So surface area, what we are calculating, it is a function on y. So first we calculate the surface area along x-axis as a function of y, because it would change. So the surface area is unique with one y value, like this. Now once we get the area in this direction, that is x into z, that is xz plane. Okay, x and z, one independent, one dependent. So in xz plane, if I integrate the equation, then I get area in xz plane with the function on y, with dependency on y. Y is independent here, whatever we get. Now whatever we get the area, that area, if I multiply the y, this area, if I multiply by y, then area into length will become volume. If I have, you remember the first case we talked, approximation. If this is the area and this is the height, then area into height is volume. Now if this is the area and this is the length, this is the area and this is the length, area into length is the volume. Okay, or I can go this way also, that I calculate the area in yz plane. So from here at one x value, here, so many cuts. So at each x, I have different area. So area in yz volume. If this area is multiplied by width, that is along x direction, then it becomes volume again. But this area will have dependency on x. This will be dependent upon x. This area will be dependent upon y. Okay, so two integration, one integration in xz plane, whatever comes the formula equation, then again integration into xy plane. Here first integration in yz plane, then integration into yx plane. So first calculate the area into width is volume, or calculate the area in xz plane, area into length is volume. But first area may be in the function of y if it is like this, maybe in function of x if it is like this. Okay, so before we proceed in kind of 4D, so we are talking now is if z equal to fxy, it is 3D, because we have independent component along x-axis, xy plane, and then we have dependent component. It is 3D. Okay, we will proceed in 4D. Then we will proceed in cylindrical, in kind of radial fashion, cylindrical fashion, conical fashion, spherical fashion. So these are cakewalk. If you understand the basic concept of addition only, okay, so calculus is nothing but basic way of addition only while calculating the area. That's it. That is the integration. Opposite of integration is differentiation. So the equation what we get, that equation we multiply. So equation what we get, that is the vertical. That vertical, if you multiply by the independent component, dependent component, independent component, it becomes area. That area is nothing but addition. So this is what we say. So dependent component is rate of change in integration. Rate of change into independent component becomes the total collection, total addition. Okay, total addition to rate of change is differentiation. So if I have total collection and if I want to know the rate of change, then I have to differentiate. Whatever rate of change I am getting, that is the dependent component. That rate of change multiplied by independent component is the area, that is integration. So two way to integrate. If I calculating the area and I am happy, then it is 2D. If I am calculating the area and that area by length, then it is we are calculating the volume. In that case, it is 3D. 3D calculation volume is of two types. One is if I have XY plane, then various rectangle we subdivide, and each rectangle we see the vertical component. So vertical into that area is the volume. Or other ways, if I know the fxy as algebraic function, then xz plane area we calculate and then we multiply it by length, or multiply it by length means we calculate the integration. One integration to calculate the area in xz plane, another integration to calculate the volume along the along the y-axis, or we calculate the area along yz plane, one independent y and one dependent z. Then we finally calculate the 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 area along the yz axis. This area, then again we integrate along the width, and then we get the volume. So this area is a function over x, so we integrate. This area is function over y. Now we came to a semicircle. Let's imagine. Oh, I'm sorry. In mathematics, there is nothing called imagine. Everything is perfect. So let's think. What is the? Let's consider, or let's talk about the equation of the circle. So circle is x square plus y square equal to radius square. That is the circle. Now x square plus y square equal to 9. So, because radius I have taken is 3. If I have taken radius 3, okay, so if this is the semicircle, then this diameter is 6, okay, and this point is origin. This point is origin, and this is minus 3, this is 3. Okay, now this is in xy plane. So from here to here minus 3, and here to here 3. This is origin. From the this is origin, then from origin it is like this. Now from if this is the origin, from origin to everywhere it is 3. This radius is 3. Now idea what I am talking is, suppose that at any point, okay, at any point the height, so this is 3D, okay, so this is 2D, and it has a 3D. 3D in the sense, from the center, if I see the y, so if this is the center, if this is this, okay, so if this is the center, if I go along the y, then height is increasing as y is increasing. So along x-axis there is no height. But if I take y as 2, then height of the 3D is 2. Height equal to y. fxy equal to y. fxy equal to y. So at any xy, the height is y. So the height is maximum at this end because it is 3. So height is 3. Okay, at any point I have to calculate the height from the base. Okay, if this is semicircle, I put it into xy plane. Now if it is in xy plane, then then from here there is a height. From here height is 0 and height is growing in this direction. Height is proportional to y. So fxy equal to y. So here, okay, here the height is 3. Whereas here, if y is 1, then height is only 1. So from origin, height is 0 and height grows like this. Okay, now idea is that calculate the volume. Okay, so now the volume is fxy dy dx. fxy is the height and dy dx, or dx into dy is the area. Area into height is the volume. Double integration. So first we have to integrate with dx, and then whatever comes as dy, then dy. Or so double integration. One integration. fxy dx dy. So inner integration is integration fxy dx. Whatever comes, that integration with dy outer integration, two integration. Inner integration is fxy dx. Whatever comes, that suppose it comes as gxy, then gxy dy. Fxy dx, whatever integration comes, suppose it is gxy, then integration of again gxy dy. Or we can integrate in other way. So what we are trying to do is fxy into dx into dy. So dx dy is dA, that is area. Dx into dy is area. Area into fxy. Fxy is the height. So area into height is volume. So fxy dx dy is volume. This is what we are trying to calculate. Dy can happen before dx or dx can happen before dy. As per this, integration would shift. Inner integration and outer integration would shift. Now, what is the integration? Now, I say fxy. Fxy is y. Fxy dy. First, we will calculate dy because fxy is in variation of y. We can do other way also. Okay. So, I believe we can do it in other session. You can do. So now we have kind of, or will proceed. It's tempting, right? Miss. Okay, so now I have fxy. So fxy is y. So if it is y, then I will integrate. If this is the semicircle, then I have to calculate. I have to calculate yz plane. So yz plane, if I am calculating, then limit will be the base y and this y. Okay, limit. So base is 0. Okay, the base x is base y is 0, whereas this y is in function of x. So x square plus y square equal to 9. Then y equal to 9 minus x square square. So if I integrate fxy dy, then lower limit is 0 because this base y is 0 at this point at the base. And then here the y is 9 minus x square square root. Means if it is x is 0, then y is, if x is 0 here, y is maximum. Okay, here x is 0 because this is the y axis. X is 0 means y is maximum, that is 3. But as we move along x direction, y will decrease. So when x is 3 or minus 3, y is 0. So fxy, that is y, y dy integrate, that is inner integration. So fxy dy, whatever we get, that is gxy. Then gxy we have to integrate again with the dx. Okay, so fxy dy, so that is y dy, integration from 0 to the upper limit is 9 minus x square square. Okay. Okay, upper limit is 9 minus x square and base is 0. So 0 to 9 minus x square square root y dy. That will come as y square by 2. Y square by 2, if I place this, then the lower limit is 0, so it has no significance. Upper limit is 9 minus x square square root. This will come as 9 minus x square by 2. 9 minus x square by 2. 9 minus x square by 2 is a function on x. This is what we are saying. So the area what we calculated now, fxy dy is the area. Area comes as 9 minus x square by 2. If x is 0, at that point area is, okay, so 9 minus x square by 2, that is the area we are talking. Okay, so if, what if x is 0 and what if x is, okay, so what is if x is 3. Okay, as per that we will have the area. Okay, if x is 0, okay, at that point what is the surface area? It looks like it comes as maximum. And when x is 3, then what is the surface area? Okay, now y square by 2, that is the integration. So 9 minus x square square root, okay, by square by 2. So it will come as 9 minus x square by 2. Now I have to again integrate with the x. So x is minus 3 from 3. Minus 3 to 3. So 9 minus x square by 2, if I integrate, it will come as 9x minus x to the power 3 by 3 whole by 2. 9x minus x to the power 3 by 3 by whole 2. If that is the case, now lower limit is minus 3, upper limit is 3. So upper limit is 3, then 9x will become, so it will be 9x, so 9 into 3 minus 3 square by 3 by 2 minus, in bracket, minus 9 into, okay, so minus 9 into 3 minus 3 square by 3 divided by 2. So either it is x or x to the power 3. So if lower limit is minus, and then it will be same thing, it will be coupled again because we are doing again minus. So 9x minus x to the power 3 by 2, 2 will go away because minus 3 to 3. So at the end it will come as 9x minus x to the power 3 by 3, that's it. So 9 into 3, that will come as 27, minus 3 to the power 3 by 3 will come as 9. 27 by 3, 9. 27 minus 3, 27 minus 9, that will come as 18. So the volume of this 3D is 18. But we'll see more on in this example. Okay, so that is the concept, and uh, it's hot. Okay, so we'll have something, but prior to that, we will proceed in the kind of our social science area. Okay, so anyway, in the integral calculus, with this example only, we will proceed on.